Go.
Alright, so my project is all about parallel programming, which is how we can write our software to execute many times faster by distributing its work across multiple microprocessors. Specifically, what I have done is I have developed a new parallel programming tool that analyzes programs while they execute using new dynamic analysis algorithms which I developed. And based upon the output of these analyses, you can rewrite the program to better execute in parallel. Currently, my tool can compile the code to execute in parallel across multi-core machines, across clusters of machines, and you can even write code for your graphics card. What I would like to talk about during my presentation is I would like to talk about what the dynamic analysis algorithms are and how they work. I'd like to talk about the results that I got when I tested my automatic parallelization tool against various applications and libraries and routines. And I would also like to talk about what I'm doing right now to put this into the real world, because I think that this sort of software could really make a difference in the parallel programming area. So the way that my software works is it instruments the target program, inserting calls to this runtime environment which I developed, which analyzes the patterns of memory accesses and determines, based upon the memory accesses, whether or not regions of code could safely execute in parallel without race conditions. This analysis will also privatize data. So, for example, it will automatically find areas of memory where two parallel regions write to and will replicate that so as to make it so that they could execute at the same time in parallel. After that phase of the dynamic analysis, it profiles the program. So I run a profiler, and this profiler determines both memory usage and the amount of time it takes to execute each region, while also performing what I call a parallelism dependency analysis. Parallelism dependency is a generalization of control flow analysis which I developed, and my profiler automatically performs this analysis. Based upon all of these analyses, my tool will automatically determine what can run in parallel, what is a good idea to run in parallel from a performance perspective, and how to rewrite it to run in parallel. This is a big improvement over existing automatic parallelization technologies, because, for example, existing automatic parallelizing compilers would only target one specific implementation of parallelism, and they would not solve data dependency analysis in the general case. They relied upon static analysis, which was quite fragile and could not handle things like sophisticated recursion or pointers or dynamic memory allocation, all of which are handled by my dynamic analysis runtime system. So in essence, what I've done is I have solved this in the general case. I've made it so that automatic parallelization can handle whatever sorts of programs you might throw at. So I've also developed some auxiliary technologies that go along with this dynamic data dependency analysis. For example, I developed my own software distributed memory system, which simulates shared memory across a cluster. And what's unique about this is that it will actually tune itself to the conditions of the cluster in order to achieve optimal performance, which existing solutions such as Treadmark's and Intel's cluster OMP would not do. So they would suffer performance degradation as the cluster got bigger, whereas my tool does not, because it targets this new software distributed memory system. I also developed a formal system, so a mathematical theory for describing the dynamic analysis algorithms, and I achieved what is called a soundness result. So I proved semantics preservation for terms in which the data dependency analysis says can execute safely in parallel. I tested my tool on quite a few programs, over 20 of them actually. The most interesting ones, I would say, are the NAS benchmarks, which is a suite of 8 supercomputing applications which were parallelized by hand by software engineers at NASA. These come in both serial and parallel versions. So what I did is I threw my tool to serial versions and it automatically parallelized them, and on average achieved 94% of the performance as had been obtained by hand by engineers at NASA. But of course mine was automated, so you didn't have to go through there and write all the code yourself. You just metaphorically click the parallelize button and it does it all for you, and gets performance that's about on par with what you can get by hand. In a quarter of the cases, my tool even exceeded the performance as had been done by hand by these engineers at NASA. I also parallelized, for example, the GNU scientific library, some machine learning libraries, some linear algebra routines, physics simulations, simulations of the flocking behavior of birds, that sort of stuff. And this is really the first example of automatic parallelization being taken into the real world and parallelizing real applications and libraries, and producing the first parallel implementations of these. For example, my tool automatically produced what is the first parallel implementation of the open source fast artificial neural networks library. So my tool automatically made that go several times faster on multi-core machines. So that in essence is what my project is, how it works, and what my results were. And so here's what I'm doing to put this into the real world. I think that this sort of technology could make a real difference in parallel programming, which is an increasingly important area as we move into this multi-core era. So what I've done is I've contacted the Intel Parallel Studio team, which coincidentally happens to live quite close to where I do. And this was about a month ago, and I presented my work to them, and they've since hired me to continue my research and implement this within the PIC framework, which the rest of Intel Parallel Studio does. So I'm working right now to try and put this into Intel Parallel Studio, and I'm working with them. So I really want to put this into the real world because I think it can make a real difference.
Can I ask questions?
Yeah?
Your software, did you test it? Is it for multi-core or is it parallel processors?
It's both. It's for... Yeah, it's both.
Yeah.
You finished?
No, I asked him a question.
Okay.
You can finish answering.
Well, it's for multi-core processors as well as multiple microprocessors.
Oh, okay.
It can also do graphics cards, and it can do clusters. And it can do clusters of these things that happen. So like I've got a 5-machine cluster, each of which has two processors. My software automatically converted, for example, a 3D graphics application to distribute its work across these 5 machines, and then split up the work across those 2 microprocessors after that, and the application went 8.7 times faster.
Wow.
All automatically.
Okay. And then the parallelizing, do you modify the source code, or do you compile it and then modify the actual static linking and how it works?
It's at the source code level.
Oh, so your system analyzes the actual source code and then it changes some things to make it parallel? Okay.
It does it at the source code.
And what language was it?
Currently it's for C, but the techniques could be adapted to pretty much any language.
Yeah.
So parallelizing software. When you parallelize software, you rewrite it so that it distributes its work across multiple microprocessors.
So it's kind of like a different...
Yeah, exactly. So it's what my software is it's a tool to reorganize your software to move faster. And it automates the process of making our software move faster by
That's so
reorganizing.
cool. How long did it take you to do that?
I'd estimate that I've worked about 600 hours on this project.
600 hours?
Yeah, I started working over the summer, and I was working full-time. By full-time I mean about 10 to 12 hours a day, 7 days a week. I actually quit my summer internship so that I could work on this full-time. And it's pretty much for my life for the past 6 months.
Did you have school?
What?
School?
Yeah, I have school. I mean, I wasn't putting in 12-hour days while I'm going to school.
Oh, okay.
But on the weekends, yeah. Right. And pretty much every weeknight.
Wow.
When did you play Frisbee?
What?
When did you play Frisbee?
Mondays, Tuesdays, and Thursdays starting about a month ago.
What did you do last year? You did a project last year, right?
Yeah.
How similar was it?
Last year's project was a theoretical project into the design of programming languages, and it did have some applications to automatic parallelization, but I'm not using any of my results last year in the area of automatic parallelization.
Okay, I'll